Okay, let's look at an application where we would need to combine K values. Coupling a non-favorable reaction with a small K value with one that is highly favorable with a large K value is a common way to drive a process toward products. For example, COOH3 solid is rather insoluble. You can see here this very, very small KSP shows that the products are not favored at all. But it can be made more soluble by coupling it with a reaction that forms the complex ion or the complex compound CONH3 okay? So that cobalt 3 plus 6NH3 produces that complex ion there. Has a very, very high favorable K value for the forward reaction. So if I put those two together, I get an overall value of K equal to 7.2 times 10 to the minus 13, which is much larger than the original 10 to the minus 44. So, how do we calculate K when initial reactant concentrations are known? Changing amounts of reactants and products in a reaction are often best kept track of in what's called an ICE table. An ICE table is constructed by creating 3 rows, one for initial concentration, I, one for the change in concentration, C, and one for the concentration at equilibrium, E. A column is created for each substance that is included in the equilibrium expression. In general, the reactions are written first, followed by the products. When initial concentrations of reactants are given, those concentrations are put in the initial row for the reactants, and zeros or dashes are placed in the initial row for the products. A variable is then placed in the change row based on stoichiometry. Reactants lose concentration at a rate based on the coefficients in the equation. If the coefficient is 1, then the change is minus x. If it is 2, minus 2x, and so on. Similarly, products will gain concentration on the same basis. So rather than minus x or minus 2x, you might see plus x or plus 2x. So let's go through an example. Given the following reaction, what are the concentrations of all materials at equilibrium, given an initial HCl concentration of 0.5 molar and a concentration of HCl at equilibrium equal to 0.2 molar? So I start out with my 0.5 molar HCl initially, and I'm told that I have 0.2 at equilibrium. So that's a decrease equal to 0.3, right? 0.5 minus 0.3 is how I get this 0.2. Given that HCl's coefficient is 2, we know that 2x is equal to that change, or 2x equals 0.3. Since 2x equals 0.3, x equals 0.15, which is the amount gained for both H2 and Cl2. So we see in red the amounts of both reactant and products at equilibrium. K can then be calculated from those equilibrium concentrations. The reverse process can also be done. If you know the equilibrium constant, you can use it to determine the concentrations of substances at equilibrium. So, given that there are initially 0.2 atmospheres of HCl, what would be the pressure of all gases at equilibrium given the reaction below? So I have my reaction balanced for stoichiometry, and I know that Kp, the equilibrium constant for pressure here, is 0.67. My initial concentration, my initial pressure of HCl is 0.2, so I put that in the I column, and I leave it blank for the 2 products because we don't start out with any products. Now my change, so if my variable is x, I have minus 2x for the HCl. The 2 comes from the coefficient, and x is just because I don't know how much it changes by. But if it decreases, then each product is going to increase. They both have coefficients of 1, so we just have plus 1x and plus 1x. So what is the equilibrium concentrations? So we have 0.2 minus 2x, and we have x here and x here. Okay? So Kp, or 0.67, is equal to the pressure of the products, which is x times x, or x squared, divided by the equilibrium pressure of the reactant, which in this case is 0.2 minus 2x. So 0.2 minus 2x raised to the power of the coefficient, which is a square, because we have a coefficient of 2 here. And so we can take the square root of both sides. Since the x squared and the 0.2 minus 2x is also squared, we just take the square root of both sides and we get 0.82 is equal to x over 0.2 minus 2x. And then do a little algebra to solve for x, and you get 0.062 atmospheres. Now, you have to remember what x is, okay? So x is this variable here, which is the equilibrium pressure of Cl and the equilibrium pressure of H2, which is why we have those equal here. And then we put x in right here to find the equilibrium pressure for HCl. So 0.2 minus 2 times x, or 2 times 0.062, is 0.12 atmospheres. So if we know the equilibrium constant and the initial concentration of our reactants, we can use an ice table to find the equilibrium concentrations or pressures. Here are some general tips for solving most equilibrium problems. First, start with writing a balanced reaction including states. Then, write a proper ice table, being mindful of stoichiometric coefficients. Finally, write a proper expression and solve for what is required. What would be the equilibrium concentration of hydrogen gas given initial concentrations of 0.2 molar for both the CO and H2O? So I start with my reaction and my known K value. I put my initial concentrations of reactants, 0.2 molar, and we start with no products. Now we have 1 to 1 to 1 to 1 stoichiometry here. So each reactant will decrease by some value x, and each product will increase by some value x. So at equilibrium, each reactant will have a concentration 0.2 minus x, and each product will have a concentration x squared. So I write my equilibrium expression. K is equal to the concentration of the products, which will be x times x, or x squared, divided by the concentration of the reactants, 0.2 minus x times 0.2 minus x, or 0.2 minus x squared, equals K, 1.56. So I have a square here on the top and the bottom of the fraction. So take the square root of both sides, and we get 1.25 is equal to x over 0.2 minus x. And then a little bit of algebra to solve for x, and you get 0.11 molar. And x, if you look in your table here, is the equilibrium concentration of H2. So that answers the question. The equilibrium concentration of hydrogen gas is 0.11 molar. All right, let's do another example, but this time with pressures. So what would be the value of Kp for the reaction below, where the initial pressure of methane and oxygen were 0.4 atmospheres, and the equilibrium pressure of carbon dioxide is 0.1 atmospheres? So I start with a balanced reaction. Notice I have oxygen and water both have coefficients of 2. So in my ice table, I start with my initial amounts of methane and oxygen, 0.4 atmospheres. And let's think of what's going to happen at the change. So with a coefficient of 1, methane will just decrease by x. So at equilibrium, we have 0.4 minus x. Oxygen will decrease by 2x. So we have 0.4 minus 2x. And again, that 2 just comes from the coefficient. And then, let's see, carbon dioxide will increase. Coefficient's 1, so by just some amount x. And water will increase, again, because of the coefficient 2, by an amount 2x. So at equilibrium, carbon dioxide is x and water is 2x. Now, we're told that the equilibrium pressure of CO2 is 0.1 atmospheres. So notice that this is x, 0.1 atmospheres. Given that, we can find the equilibrium pressures for everything else. So 0.1 times 2 would be 0.2 atmospheres. 0.4 minus 2 times 0.2 would be 0.2 for the oxygen and 0.3 atmospheres for the methane. So we have final pressures that we can just plug into a Kp expression, which again is pressure of products over pressure of reactants. So starting with the products, we have carbon dioxide, 0.1 times 0.2. Now we have a coefficient still of 2, so squared, over 0.3 times, again, 0.2 because the oxygen it should be squared. And so we put that in a calculator. These 0.2 squareds cancel, and we get 0.1 over 0.3, which is 0.33.